So here we have the dots are our observed values. And if we make a line going through them, we could see the line touches almost all the values. And if they don't touch, the dot is very close to the line. Good fit, most points lie close to the line, so prediction errors are small. So here's a poor fit regression line. Don't worry too much about the jargon going on. I just want to focus on, so the dots are over here. If we make our regression line for these points, they're all super far away. These residuals are very, very large. So poor fit, the line misses the overall pattern, producing much larger prediction errors. And you can see here we have our correlation calculated. All right, understanding the residuals. So this has the good fit, and I hope we can see it. It might be a little bit difficult to see, but you can see these little red lines from the that go from the center of the dot to the line. This is a good example right here. You can clearly see it goes from the center of the dot to the line. For a good, so yeah, each red vertical segment is a residual. Residual equals the observed value minus the predicted value, which is y minus y hat. So for here, it would be this y value minus the y value at the line. And the least squares method chooses the line with the smallest possible sum of the squared residuals. So this is an example for a good fit. For a poor fit, our residual lines are much, much greater. They're much more obvious to see here. You know, this one, the difference is 18. This one, negative 25, only negative because it's in the down direction. But the residuals are much more obvious with a poor fit least squares regression line. So comparing the two. So we're going to compare, this is just a table looking at the points for our good line versus our poor fit line. So on our good line, again, I just took the points from this table and from this graph, excuse me, and I put them on a table. So here are ours. These are our X values and these are our Y values for the points. Okay. In this column here, we have our Y value for our regression line. Okay. So this column here, we take the difference of the value here minus the value here. And you see, we just get a bunch of negative ones, positive ones, and zeros. So we square them for the next step. We really want to square them just so we can keep everything positive, and you'll see why at the very end. But we square all these up. And then after we square them, we can add them. Remember, this is sigma, which means capital sigma, which means sum of all these values. This is our y minus our y hat squared here. We add all these up, we get 7. When we take the sum of the squares of the residual, the smaller that value is, the tighter our line is. The closer your average point is to the residual line. And you can see here with the poor example, this is the data taken from this table here. These are our X values, ours. These are the Y values for each one of the points. And then these are the Y values at the hour of our line. So we take the difference of the two and we square them, and then we add them all up, and we see this number is huge, 3,844. So this large number tells us that, hey, this is not a good fit. This is a poor fit. All our residuals are huge. Going back to our correlation video, we could say that it has a weak correlation, or going back to the scatter plot video, we could say it's what's the term we use here? A weak association, if no association at all. All right, let's go back over here. So again, very weak association here. And we've just shown that with the data provided to us. The good fit model has a much smaller sum of squared residuals because the observed points stay close to the regression line. The poor fit model is still the least square regression line for its data, but the data themselves are highly scattered, producing larger residuals. And again, larger residuals, poor fit; smaller, good fit. Why square the residuals? Prevents positive and negatives from canceling out. So like here, like if we didn't square these, some of the positives and negatives would cancel out. It would make the smaller number, which wouldn't give us as accurate of a reading. gives greater weight to larger errors. So, and that's a good example with this here, because we square a bunch of negative ones and we still get one. That implies much tighter fit. And if we square a decimal number, like say, like, what's a good example? Like 0.2 squared is going to equal 0.04, which would mean it's even closer, or and give even closer information. It's even closer to 0, which means to even better fit, or represents a better fit, I should say. And then produces one best fitting regression line. Yeah. All right, and then we have the influence point. So here, let's focus on this data here with the blue dots with the blue line. Okay, if we just take these points, we have an extremely good fit for our regression line. The regression line is very close to all the observed points. But then if we take these blue points and include the influence point all the way out here, in this example, it is an outlier, but we could see how much it skews the entire line. And by including this point, our line goes from here to now here. So an influence point is an observation with an extreme X value that can substantially change the regression line, as seen here. Notice how adding 1 point changes the slope of the line. And now, while an influence point can be an outlier, it does not necessarily have to be an outlier, okay? All right, so here I have how we calculate the least squares regression line. Now you should notice that it's just a straight line, and hopefully we are familiar with slope-intercept form, y equals mx plus b. Now the complicated part is, how do we find the slope and how do we find the y-intercept? My point here is to just kind of give you an introduction to this. My next video will cover what the mathematics behind this looks like, but we do have, it's not nearly as difficult as it looks, but it's certainly not quick. But again, we'll go into this next video, but I just want to introduce it. So we can find it with an equation and some given data, or we can use a calculator. I will show you how to do this in a separate video as well with the TI-84. All right, and here we have some practice problems. Which line of regression, good fit or poor fit, would produce more accurate predictions? Explain. What does residual represent? Why are residuals squared instead of simply added together? And how does the influential point affect the regression line? Feel free to pause here and take a look at some of these questions. All right, hopefully we did that. Let's take a look. So, which line of regression would produce more accurate predictions? The good fit regression line should produce more accurate predictions, and it's because the points are closer to the line, resulting in smaller residuals. The smaller the residual, the better the prediction. What does residuals represent? A residual is the difference between the observed value and the predicted value, and we find it with y minus y hat, where y is the observed value and y hat is the predicted value from the residual line. It is the vertical distance from a data point to the regression line. Why do we square residuals? Why are residuals squared instead of simply added together? Squaring residuals prevents positives and negatives from canceling out and gives greater weight to prediction errors. And lastly, how does the influential point affect the regression line? The influential point changes the slope and position of the regression line, showing that a single point with an extreme X value can have a large impact on the model, as shown with this example over here. Cool. And that's all I have for you on regression, or what's the full title of this? Sometimes it was linear regression, least square regression line. Like I said, in the following videos, I'm going to show how we can calculate the line. Typically, we use method 2 with software or calculator, but I believe, what did I have one professor tell me? We learn the hard way before we learn the easy way, because we have to respect our ancestors, respect those who had no choice but to do it this way. So we should at least be familiar with it. Anywho, that's everything I have for you on regression line. Thank you for tuning in. As always, a link to the notes will be in the video description, and I will see y'all next time. Take care.